Secret Astronomy, Sacred Geometry on Coral Castle TV. Dank ass gear provided by the Cult Machine. All hail the machine.
Hi guys, thank you for joining me for another episode of Coral Castle TV. Today we're going to be talking about something extremely important and brand new. I think that's something that we've been lacking for a while is some new stuff, and boy do I have it for you. Now, I've teased this for quite a while, and I have had quite a while of time since I first mentioned that I made this discovery to the time that I'm making this video. I understand. I apologize. Life gets in the way. Sometimes COVID gets in the way, and there have been a lot of delays. But I'm ready to bring this to you now. In fact, I have had an iron will in the regard of getting this video shot so that we can discuss this because it's so important. It changes things. And I think that's what we really need in this world right now is we need something to change things. And Ed Leedskalnin did it 100 years ago. And that's what we're going to talk about today. What we're going to be talking about is Ed Leedskalnin's Sundial. Today I'm going to be starting a master class series on Ed's Sundial, and what it means and what it shows. Now, what's going on here is that Ed has proven astronomy wrong. Tee-hee. And I mean proven it. Proven it using their science, using their math, using their methods. He didn't use any new science. He used the science that was already laying around. And he applied it efficiently. And I think I cracked it. So I'm going to present my evidence and I'm going to present my case. Before I do that, however, what I have to do is catch people up who aren't up on this. So Ed Leedskalnin says in his written works that we should check out the drawing on the red door, that we should check out the Polaris telescope and the Sundial and see what they have to tell us about astronomy and about science. The red door. So what he shows, and I'll throw up the graphic here as I'm talking so you can look at it. It has an unusual drawing on it, and it has what looks like the sun, and then it says Earth 21, and then it has what looks like the Earth here and the Earth here, showing the apex and the apogee of our orbit, which seems to contradict what we know about science. Now, astronomers believe it to be this way. But this is how we go. But Ed shows something completely different, doesn't he? And he invites us to use the Polaris telescope and the Sundial. And what he's doing is, with the drawing on the red door, is he's saying, hey guys, this is my math. Feel free to use the instruments that I built to check my math. It's pretty cool, right? So that's exactly what we're going to do. So the first thing that we have to do is we have to ascertain what this drawing is telling us, don't we? We have to say, what is it about this that's different than the current model? And it shows it on an angle. And it also shows that there is a difference in the length of orbits. This is Earth 21, and since it's closer, I would say what he is saying there is that it's 621. And that this is 12/21. This is summer solstice, winter solstice. But there's another additional thing on there that people don't seem to talk about or acknowledge. Maybe they don't even really see it. But there's one in the middle, and this is the equinox. Right? This is the equinox here. And this equinox, since it's equal, is on both sides. So notice that it is dead center of the sun during the equinox, but at each of these extreme periods during the year, they're at an angle, right? So we see that there is a difference in the length of orbit between winter and summer. We see that the equinox lines up in the dead center of the sun, and that he has this mapped out for us on the red door. And it completely contravenes what is being said by mainstream astronomy, mainstream science, and the standard model from which we are all taught from, including myself. So to sum up, the red door shows us that his drawing has a difference in orbital length between summer and winter. It also shows that he shows a difference in the orbital angle, or the tilt, in relation to the sun. So, these two things are what we are going to focus on, and it is because he names these two things with the drawing on the red door. He's telling us to our face he shows a difference in orbital length and a difference in the orbital angle. Now, he has put in place something to prove each one of them. He doesn't expect you to believe him. He says, I built these and they defooled me. And they defooled me, and now I'm going to defool you. All right? That's what we're here to do. And the first one that shows the orbital length is called the Polaris telescope. And that's what we're going to talk about next. All right. So we have the Polaris telescope. And basically, the Polaris telescope is a 40-foot tall obelisk that was built by Ed. That's made of coral. And it has these crosshairs that are placed in it in wire. And the reason it's called the Polaris telescope is because any clear night of the year, you can look through this, the crosshairs that he has made, and you can see Polaris in one of the 4 quadrants. All right? And with this, we know we can mark the seasons. See, he has them marked off in quarters, and he hasn't even just got Polaris accurately within the crosshairs, but what he's done more exactly is he's marked the position of true north, because Polaris is a circumpolar star. Now, it is our closest pole star to exact north, but it's off by about 2 degrees. And this is exactly what Ed shows. He shows this 2-degree deviation, and it's only because he has been so accurate as to mark true north, which is a feat unto itself. But any clear night of the year, you can see Polaris, and if you track its movements, what you see is something very interesting, because if our pole is pointed at north, true north, okay, and so true north would be the sun, the central point that we revolve. And the reason that this moves from quadrant to quadrant isn't because the star moves, it's because we move, right? I mean, everybody agrees on that. Even mainstream science says, yes, it's because we move, right? So, if the star moves because we move, by tracking the star against a central point, it now becomes analogous with our own orbit, doesn't it? Now, this isn't hard to understand. So what Ed has done is he has tracked the star very closely and has given us our view of our orbit in micro, right? If you track this every single night and you track the position of the star, what you get is a kind of an egg-shaped elliptical orbit. This would be the topographical view. If we were looking at our movement, looking down on the Earth as it moves around the sun, this is exactly what we would see, because he has perfectly captured it in microcosm right here where you can see it. Now, it says it's the Polaris telescope. Wrong. Don't think of it as a telescope. It's a sextant. And what a sextant does is it marks the position of a star in the sky. And we can use these to track motion and time. And this is what Ed does. He tracks motion and time. And he does it expertly and simply. He does it with a giant piece of stone, a couple pieces of wire, and he nails exact true north. And then we see our circumpolar star, Polaris, moving around it. And so now true north can be analogous to the sun. And Polaris can be analogous to the Earth, and now you can see our motion without having to be outside to witness it. You can see it in microcosm, and this is what he has shown. And this is what backs up the drawing on the red door, at least in his one assertion, where he shows the Earth, and then he shows the Earth up here at the top, and he shows this longer orbit between here and here, then between here and here. And this bears out because this is spring, summer, fall, and winter. And it moves in a clockwise motion like this. And when you connect all the dots, what you get is exactly what he shows on the red door. So here's our one proof. One proof is over. This is kind of the easy one. Believe it or not, this is the easy one to understand. The next one is going to be a bit more challenging, but I promise you, it is the most rewarding. I feel so vindicated for believing in Ed and for staying on this trail. And I congratulate you for doing the same thing. I'm proud of you, all 17 of you, or whoever who are too drunk to go home. Bless you. It's all going to pay off in the next segment, the Sundial. Okay, so here it is. What you've been waiting for, the Sundial. Strap in, because it's about to get sciencey. And I also want to say, before I even get to the Sundial, on an interjectory note, when I was talking about the Polaris telescope and how it's really a sextant, how it's really analogous for our own orbit, and it shows our orbit is kind of like an egg-like ellipse, how come astronomers have never come down there to acknowledge this? I published this work. No one's acknowledging it. No one. And you know, it's kind of like a sign you know you're right, because when they can't argue, all they can do is shut up, right? All they can do is just sit there and take it in silence and hope people won't believe me. But you don't have to believe me. You don't even have to believe Ed. All you got to do is understand the principles of basic science. That's all you have to do. And Ed shows it to us so clearly, so plainly, that I think it's almost like lost on us how simple and clever and concise and right that it is. And, you know, sometimes people want to throw out the message because they don't like the messenger. Well, hey, sorry. You know, you get me. And that's all there is to it. Now, I try to be nice and I try to do my job as best I can, you know, but if you don't like my personality or my hat or whatever, you know, hey, whatever. If you're going to let that stop you, then you're not scientific anyway. If the tattoos confuse you, just realize that people can be smart and have a personality at the same time. I know, it's crazy, right? So anyway, on to the Sundial. Now, it's very important to understand that Ed, I love him, and a little guy from Riga, Ed was a liar, okay? Ed was a spy. Ed was a secret keeper. And there seemed to be no links that he would not go to in order to keep things secret. He would lie to you right to your face. And this is what a magician does. And this is why, even though I know there's a famous chess player, I believe it was his name, Mikhail Tal, who they called him the magician from Riga. Well, Ed is also the magician from Riga. He is the next one. Because he would lie to us right to our face. You know, for instance, he called the Polaris telescope a telescope. It's not. You know, there's no magnification. It doesn't bring the star in closer. You can't do anything except track it with crosshairs, which is exactly what a sextant is. But he calls it a telescope and people don't know any better. Then he lies to us again. Oh, tricky Ed. Tricky Ed calls the sundial a sundial. When, it kind of is, I guess. I mean, I'll be honest, I've been there 4 times, okay? 4 different seasons. And do you know that I have never found that sundial to be especially accurate? I checked my watch, you guys sound like, you're off by a bit. But I realized that this is the clue. Everybody else wants to have this folklore that I don't understand, where they're like, oh, I checked it against my watch and it's perfect. Like, look at the picture I took, when what you did was you moved your clock, you moved your watch ahead about 10 minutes. So it was right, and then lined it up to propel this folklore. And my job, and it's an unpopular one, is to dispel folklore. And every time I've been there, in every season, it's not been especially correct. And then I started noticing something. Well, I noticed that there's a chair on top of it that's sideways, like looking down like this at it. Yeah. And then it hit me. Oh, no wonder it's not right. I'm looking at it wrong. I'm not looking at it from the place he intended you to see it from. You can't check the time accurately standing down on the ground looking at a curved surface at an oblique angle. You can't do that. There's parallax view, there's shift, there's all kinds of problems. So what we have is we have the answer staring us right in the face, and it's the chair on top. He's telling us this is the angle to look at it from. If you want to know the time, sit in the chair and look over your left shoulder, and there you go. You can see the accurate time. But even then, it's not tracking time. It's tracking star time. It's called sidereal time. Okay, and this is why we're off by about 4 minutes a day. Our day's like 23 minutes. Or 23 hours, 56 minutes, 29 seconds, something like that. So we're off by about 4 minutes a day. And after those days add up of all those 4 minutes, well, then now we have to do a shift to our calendar. We have to go an hour back or an hour forward in order to make up for this difference between the sun time and the time, right? So Ed's keeps perfect sidereal time. So if your watch isn't right, well, it doesn't matter what season and how many of those 4 minute days have passed since this was exactly correct. And we'll get to when it was correct. But that's the main point. And so I started realizing that, Ed isn't, again, he's lying to us. He's fooling us. And what he's saying is I built a telescope and a sundial. And what he built was 2 sextants, right? Because if you boil down what a sundial is something that tracks the position of a star in the sky. Does it not? Yes. So these are both sextants that he is using in order to make his astronomical assertions on the red door. Now we have the first proof, and it's indisputable. And I challenge any astronomer to prove me wrong. Lie to me. Go ahead. We can fight about this because the proof is at the Coral Castle. All you got to do is set up a team down there and track that star through the crosshairs, and you will have a perfect analogous orbit of the Earth around the sun in a year. And what it shows is exactly what Ed showed on the red door. Shorter and closer orbit in the summer, longer and farther away orbit in the winter. And then I'm going to go even farther and show you why this happens and some other stuff it kind of lines up with. But here we go. So the other interesting thing to me was the gnomon, which is it's the little piece that sticks out on the sundial that captures this, throws the shadow. And I realized something. Hold on, I'll get my eraser here. But I realized that there was something about the gnomon that was strange. When you look at most sundials, they come to a point, right? They just have a single point. And you can more easily clock the time. There's only a single point, or 1 degree of angle of the sunlight that is being caught. 1 degree, right? So you have this single point where the sun will hit right there at that tiny point and give you 1 degree. And this is apt to be the least accurate sundial, because it's only going to be right 1 day a year for a little bit, because we move off from a single point. We deviate quite a bit. And this is what Ed Leedskalnin shows. And if you look at this gnomon, it's 1 degree, and then you look at Ed's gnomon, how many degrees do you see? Go ahead, stop the video if you want. Take a second, look at this gnomon, and then look at this gnomon, and tell me how many degrees there are in this gnomon. I'll wait. All right. So, if you came up with the answer of 360 degrees, pat yourself on your smart little back because you got it right. That is correct. Where the general gnomon shows 1 degree or casts a shadow of 1 degree, we have a gnomon here that has 360 degrees. Don't believe me? Well, here's a 90-degree angle here. Here's a 90-degree angle here, a 90 here, and a 90 here. And 4 90s adds up to 360 degrees. So this means, then they say, oh, well, it's accurate year-round. No, it tracks it year-round. See, it's only accurate if you know what the sidereal time is. If you look at your watch, it's bound to be off a little bit, unless you happen to be there on a single day. I'll tell you what that day is later. But this is what we're dealing with right now. We're dealing with the difference in a sundial between 1 degree and 360 degrees. Now, 360 degrees, the last I checked, and maybe Neil deGrasse Tyson or somebody can correct me if I'm wrong, but the last time I checked, 360 degrees was a complete circle. Right? So he is tracking the sun through 360 degrees of motion. This isn't hard to understand, right? And so what do we have? So I realized I knew what he was doing. I've seen this. I've seen this before. I saw it in school. When I was in school getting a technical degree. It was in computer-aided drafting. And so one of the very first things you learn are about the axes, the planes, right? You have your X, your Y, and Z, right? The 3 planes. And this is what Ed is very cleverly doing. All right, let me explain. So, if we want to plot a point in space and locate it and say this is where it is, all right, we have to do it in relation to things. Relation to things that are permanent and make sense. All right. So this system of X, Y, and Z, the 3 planes, are known as Cartesian coordinates. Okay? Cartesian coordinates. And it was when I saw the chair that I realized, oh, now it makes sense. Because that's what he's doing. He is mapping the star, our sun, using Cartesian coordinates. And I'm going to show you how detailed this gets. It's amazing. So, by the way, this is a scale model of the gnomon. This is an exact scale model, which I used by basically one of the pictures I took of the gnomon, and I scaled it up. And then I copied it, and then I made a template, and there it is. And we will get into the mathematics of this, but I would like to get first into the Cartesian coordinates and fixed plane geometry. I think that's a good enough introduction before we get more complicated. So, we want to plot something. What we must do is we must establish these planes. And these planes must be aligned with something that we can hold to, right? So, Ed builds his sundial on a curved surface facing south. So, north, south, right? West, and east, right? Easy. Now, because he has the gnomon, he's marking his position. And so what Ed is doing with the gnomon, a 360 degree gnomon, and Cartesian coordinates, is he's mapping out the path of the star as we move around it year round. And here's some additional proof. So we have his sundial, which is built on a curved surface. And I'm going to tell you why it's a curved surface, because people can't figure this out. They're like, well, why? Now, I'll tell you why. It's because he needed to build a sundial. See, because he knows where true north is, right? So if he knows where true north is because he made the Polaris telescope and it's accurate all the time, then he also knows where true south is. So now we have these two fixed points. These points are fixed. And they're fixed perfectly, right? So in order to capture the sun, you have to build the sundial facing south. South is how we catch the sun and how we can see it move across the horizon. So he wants to do this accurately with Cartesian coordinates. So what he does is he builds a sundial that's 90 degrees perpendicular to Z and to X. So we have this 90-degree facing the south facing sun, right? And what he's doing is he's using the gnomon like this. Okay? This is what the gnomon represents. It represents this field in Cartesian coordinates. Because he's fixed north and south, he's made a 90-degree angle to catch the rays of the sun. And then now, as it moves throughout the year, he has the only movement will either be along the z-axis or along the y-axis. Because this one, x, is fixed. So, he has a fixed point at a 90-degree angle perpendicular to the angles that he wishes to measure. And now, because the gnomon is correct, means he's measured it accurately all year round. There's nothing to even argue here. So, here's what happens, is we have the sun at each of these points for every season. Just like he shows in the Polaris telescope in the crosshairs, right? So, he has captured the path of the sun by the analogous orbit of the Polaris telescope. And then he shows that he has created a gnomon which captures noon at every season. Isn't that strange? So he had to have a starting point. He had to have a baseline, right? So this is where, oh, by the way, once we understand that he is using Cartesian coordinates, now we can put this, we can convert this into convert this into a graph of a vertex form, mathematically. Now that we have this data, we have the size and relation, the proportion of this. Now we can assign values and we can math this all out. But for now, I just want to give you the fixed plane Euclidean geometry that is just absolutely irrefutable on its face, and then we can get into the details of what the math means later. But right now, what I'm showing you is science. This is Cartesian coordinates, and these are 360 degrees, which is analogous of our orbit. It is showing if it's right all the time, as people claim, and it is close. It's close to regular time, but it's absolutely right sidereal time, because tracking the star is the only thing it does, right? So we had to have a baseline. He had to have a time when everything's in balance, where it's equal day, equal night, according to his theory, equidistant to the sun. Oh, you know, it would be a good day. Back in his time, September 10th, 1923 would have been the perfect day for that. Don't you know it? The day of the autumnal equinox, total solar eclipse, and Venus and the sun all aligned, equators all aligned with Venus in the occult phase. So a 4-point syzygy, when everything is in perfect balance and alignment. And that would have been the perfect time to do that, wouldn't it? Huh. I wonder if he knew about that day. Sorry if I'm yelling. I get emotional. But anyway, what we have to do is we have to start analyzing this with regular geometry. Let's just say it plain. Like, what does it come out to? And you know, here's something interesting. Here's my template that I made out of Me Lucky Charms. Don't tell anybody. Don't make fun of me. Shut up. But the point is that we have to start looking at this from a standpoint of just simple geometry. Just plain fixed geometry. And say, well, Ed says in his written works that he says we slide axis way. So what he says in contravention to modern astronomy is that where the Earth goes around the sun, scientists say it does this, right? And what Ed says is that we do this. That's what we do, right? And he's right. He's right. We slide axis way. We are at a 23-degree angle, and we move in relation to the sun at a 23-degree angle. Oh, how do I know? Oh, well, because if you take this gnomon and you draw a line from here to here, put that on a protractor, guess what it comes out to? 23 degrees, 23 and change. Do the experiment yourself. Make yourself one of these expensive templates. I'm happy to sell these. They're $100 a piece because it means I have to eat an entire box of cereal to make you one. And if I'm going to get that fat, I might as well get paid for it. Now, this is 23 degrees. This is exactly the orbit that he describes. He shows if this is right here and it's right here, if north and south are fixed and the only motion is on the z-axis and the y-axis, if the only way it goes is up or down or side to side, then it is not us that is moving, because what he's done is he's fixed. He's fixed our poles. He's aligned with the poles, so the poles will not move in his experiment. So the only movement has to be us in relation to the sun. And therefore, we are at a 23-degree angle and we orbit at a 23-degree angle. But I'm not done. It gets a little bit complicated. It's kind of tricky, but I think you guys can handle it. I should have stopped the video a long time ago and let you digest this, but I can't. So you got to bear with me. You're just going to have to pause it, get a drink, whatever. So while I showed the gnomon, the way it is, if you are looking at it from the top down, which is the correct way, the right way is the opposite. So it would be like this. I'm going to do this fast. I don't want to waste your time here. You understand what I'm saying? All right. So we have our gnomon. And what we have to do is we have to look at the gnomon and its relation to astronomy from the viewpoint that it is looking from. See, we're looking at the gnomon from the top down, the way the sun looks at us. But no, to understand it, we have to flip it and look at it the way that we would be looking at the sun in order to understand. And if you flip the gnomon, then that's what happens. And we still, of course, have this exact same angle here. And we also have something else. We have these 90-degree angles that need to be reckoned with, right? These are the orbit of the Earth. Each one of these corners represents a season. And the center represents the sun. Starting to make sense now? So, when we have this orbit, what we do is we just connect the dots. And now what we have is our true orbit in relation to the sun. And this would be summer, this would be spring, this would be winter, and this would be fall. If you've been following along with the home game at all, what you realize is that he's created another set of crosshairs, hasn't he? He's set the points, right? And when we connect them, when we connect one here and one here, using the Y and Z axes, what we catch is our motion, because the sun is going to be right here in the center, isn't it? That's the center of the crosshairs. Just like how he marked the analogous sun with true north, again, locking our coordinates to track motion, right? And you're able to see through the crosshairs the motion of the star, which symbolizes us. So what he did was he used true north to symbolize the sun, and Polaris is us. It can be no other way as far as what it shows in the crosshairs. How it orbits through the crosshairs is how we orbit around the sun. It can be no other way. No astronomer can argue with this, yet they refuse to acknowledge it. And he's done the same thing with the so-called sundial, the other sextant, because he's marked our position topographically and orthographically, right? So he gives us the top-down view, and then to be complete to know our orbit, we need to know the side view, right? So that's what the sundial or the sun sextant is giving us here with these crosshairs, because we have at each point, this is the Earth, this is the Earth, this is the Earth, and this is the Earth. The sun's in the middle, and as we travel around it, our angle changes. And it gives us these crosshairs where sun in the middle and then the Earth at each point. And what we see is that this is a 23-degree angle. However, a 23-degree angle to what, you may be asking? At least I asked. A 23-degree angle to what? Well, this is where I got to pull out the heavy graphics. All right. So, you may be asking yourself, 23.5-degree angle of orbit to what? How do we know it's at an angle? To an angle to what? Right. And this is an easy answer, at least according to Leedskalnin physics. The answer is magnetic polarity. This is easy because the sun has a north and south magnetic pole, does it not? The Earth has a north and a south magnetic pole, does it not? Yes, it does. So what we are saying is that our magnetic angles are at a 23-degree angle to each other. That's what we're saying. And that this is perpetuated not only in the orientation of our daily rotation, but also in our orbit around the sun. So we'll have the Earth down here representing summer, right? And we'll have this up here representing the winter. I know that's a little bit out of proportion there, but I'm just trying to show that there is a difference between them. Now, look at what happens, right? Not only does our distance to the sun change according to Ed's very accurate megalithic instruments and the readings that they give us, but it also changes our magnetic orientation to the sun. This is huge, okay? And the reason this is huge is because this feeds into his philosophy. This proves him. You understand? He talks about how we need both north and south magnetism to thrive, for life to thrive on the planet or in general. And what do we see? We see not only changes to the distance and the length of time that we may spend at that distance and the angle of our orbit, but we also experience a change in magnetic orientation according to our fixed spot. So, for instance, I live in the northern hemisphere. So, in the summertime, the northern hemisphere is getting all of this southern magnetism, right? We're completely saturated by the solar magnetism that comes from the sun and delivered in the form of heat and light, right? Now, the southern equator down, well, they get all southern exposure, no northern exposure of the sun, and therefore things shut down. See, south and south don't work. North and north don't work when it comes to life, like plant life, things like that. So they shut down. They hibernate. They have no choice. The magnetic energy that they need is being taken from them, and so they slowly collapse like a flam in a cupboard. Here. Now, we change our magnetic orientation, and we move through space. Now, we keep our same angle, but we just traverse a straight line along that angle until, boop, then we end up right there. What's this? This is the equinox, right? This can be either the autumnal or the spring equinox. It doesn't matter, because they're both going to be when our equators are aligned with the magnetic equator of the sun. You see, because here's our magnetic pole, here's our magnetic equator, and here is how it relates to the sun. This is a very powerful time, by the way. And I believe that this is one of the secrets that Ed Leedskalnin knew and used in order to build the Coral Castle, that he was able to exploit a loophole that happens when these magnetic equators line up with each other in a row, like the trigger mechanism on a Gauss rifle, where you give this one a little push and it pushes them all. And on the day that he shows, September 10th, 1923, there would be Venus back behind here. Venus is in occult phase. And then the moon in between the Earth and the sun, and then the Earth. And on this day, guess where Ed was? Ed was right there. Ed was right there on the opposite side in the exact spot where that kind of thing could happen on that day. The day he carves into the wall, the day he used to set the sundial. Is anybody getting this? It's important, you know? And so now we travel past our equidistant from the sun with our pole at a 23-degree angle and our magnetic equator aligned at an angle but still centered. And then we move into winter with that same line. And now look what happens. Wouldn't you know? Now we have this southern hemisphere is getting all kinds of northern magnetism, right? It's not getting any of the southern, right? It's getting northern magnetic exposure from the sun, and guess what? During our winter, it's their summer. You see, it doesn't have anything to do with temperature. It has to do with magnetism. And so if you look in northern hemisphere, we're getting all northern magnetic exposure of the sun, right? we're getting no southern magnetic exposure. So everything is northern exposure. Northern and northern don't go together. And guess what? Things have to shut down. Things change. Things hibernate. Things die. Right? And then we come back around. As we start our descent, our magnetic, and we go from being farther away to closer, and we also are changing our magnetic polarity to the sun as we go back down. This would be spring, back when things balance out again. Only this time, instead of things shutting down, they're opening up because we're changing our magnetic exposure to our benefit by getting that southern exposure from the sun to our northern hemisphere. So those two magnetisms can interact and intertwine and exchange. And that's when things can happen. All of this. Two pieces of stone. Ed Leedskalnin deserves a posthumous award. He deserves recognition. This man is defooling us, and he did it cleverly and simply and beautifully. Excruciatingly good. And next year will be the 100-year anniversary of the Coral Castle. So my question is, I've done my homework. Okay? What are you going to do? What are you going to do to help? Will you pass this video along? Will you buy my book, The Leedskalnin Codex, Breakthroughs in Understanding the Coral Castle, where I talk about this? Only I expound a lot more on the Sundial part. I had been stuck there for quite a while, but consider that book the companion to this video. Drop a like, subscribe to me. If I can get 100 subscribers, I can do a live stream and I can answer people's questions live. So that would be fun. I could do a live show. I've never done a live stream like that. I think that would be a lot of fun. So if that's something you're interested in, find 12 more people as brilliant as you and drag them here and make them click a button. Okay? But I'm going to stop here for now. I think that I've given you plenty to digest, hopefully some to enjoy. I hope this excites you. I hope you see what I see. That's my biggest fear. You know, I've been hesitating to make these videos because I think, not that I'm wrong, because I got Ed. I got him locked. You know, I got this figured out. But I'm afraid that I won't be able to say it in a way that you'll be able to understand. I won't be able to explain it and I'll ruin it. And it's so much pressure, not only to be right and to be accurate with your facts and your discoveries when you're the only one who knows about them, but also to be able to bring them to you. And it just takes my autism and just like, I freak out. But I made myself do this because it's so important. And I hope I get it right. Send me questions. Ask me questions. Challenge this. I defy you. Send this to any astronomer you want, even if it's Neil deGrasse Tyson, and ask him. Ask him to defy this science. Ask him to do his homework and give Ed his due. This is R.L. Poole. This is Coral Castle TV. And that is how we do this.
Thank you for watching Coral Castle TV.